So, Bismillah, we said we're going to be starting about this basics of counting and the pigeonhole. This is the topics for today. And the basics of counting are going to be an introduction to probabilities, basically. And then if we'd like to, before we start talking about probabilities of something happen, we'd like to be able to count how many possible ways how we can do certain things, how we can do certain things and count how many times we can do them differently. Like, for example, let me just go back with the examples. For example, if we have like this example number one, a new company with just 2 employees, these 2 guys, Sanchez and Patel, rents a floor of a building with 12 offices. Now, how many ways are there to assign different offices to these 2 employees? So we have 2 employees, this Sanchez and this Patel, and we have 12 offices. Now, how many ways we can put these 2 employees into those offices? So to look at it, for example, I can have maybe represent these are all the offices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is going to be 11, and this is 12. So for example, I can put I have 12, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. So I can put, for example, Sanchez here and Patel here. Okay, that's one way. The other way is that, okay, I can leave Sanchez there and put it here. But Patel here, or move it here, and then you can see the combinations. I can just try 2 different ways how to get those. So the rule of these product rule, what it says is that if you have a procedure that can be broken down into a sequence of 2 tasks, if there is n1 way to do the first task, and for each of these ways of doing the first task, there are n2 ways to do the second task, then the result to count how many ways is to be n1 times n2 to do that procedure. Now, let me take us back to that example. So if we have Sanchez and Patel, how many ways, if I start with this Sanchez, how many ways I can put him in an office? Now I had 12 offices, that means I have 12 options to give to this Sanchez. Now, okay, once I have given to Sanchez 12, how many are remaining for Patel? 11. So the thing is, this product rule says that if you have something like, I'm counting how many possibilities for this first one, and then based on that first one, I'm counting how many possibilities also for the second one. Now, in total, how many different possibilities there are? Well, it says this is the rule. The rule of the product is that if I have something that is like this, which I have to do, there's N1. N1 is like this 12 ways to give Sanchez an office, the first task, and of doing this, the first task. And then what is remaining is that 11 ways to do the second task, which is giving Patel an office. Then this 12 times 11 is going to be the number of ways to complete that procedure of assigning the offices of these 2 people. So this is what it says. So which can be done in 12 ways. So assigning to Sanchez, this is the first one. We can choose anyone. It doesn't matter. You can choose Patel. It doesn't make sense. It doesn't make any difference. 12 ways. Then to first Patel, now we don't have 12 anymore because 1 was given to the first employee, so the second employee has only 11 of the options. So then the result is 132 ways to assign offices to these 2 employees. So that's what is it called? It's called the basic counting principle for the product rule. The product rule, because we make a product, we multiply. So when do we use the product rule? If we are using like 2, let's say 2 steps, step 1, and then the step 2 is based on step 1. So we have 2 steps, step 1 and step 2. And then this step 2 is depending on step 1. Now step 1 is assigning an office. And then once we assign an office, the step 2 is going to be affected by the step 1. So that's when we're going to be using this product rule. Now there are other examples of these. Let's try to go through another one. For example, the chair of an auditorium has to be labeled, the chairs, now in the auditorium, like a big classroom. Every chair would like to put a sticker on it with an upper letter English letter followed by a positive integer not exceeding 100, which means now every chair is going to have a letter. This is going to be a letter, and then a number that is going to be at most 100, at the maximum. That means it can be 001, 002, etc., etc. So it can be anything. So now this is the question. What is the largest number of chairs that can be labeled differently? Now, using these constraints, what's the largest number of chairs that can be labeled in that way? And now, how do we know that? What we said is that this should be a letter, and these should be the different numbers. So in here, how many possibilities for the letters? Well, we have 26 for the English. That means 26 letters. This is what we have. Now, with each one of the letters, how many possibilities that we have? Well, we have 100 possibilities because we have the maximum we said is 100. So 000, or maybe 001, 002, 003, until 100. Which means now I have 26 times times 100 different ways how to get numbers. That means the biggest number that I'm going to, the biggest number of chairs that I can be using this system to label is 2600. So that's why we have these 26 letters in the alphabet. And then we have 100 possibilities for each one of the letters. And then the product is going to tell us that we multiply these two, it gives us 2600 different times, different ways how to have a chair labeled. And therefore, this is the maximum we can use. Now, if we have a room that has more chairs, this system is not going to be enough. With this system, we can have this maximum number of chairs. So that's basically what it says. If I have like two things that are one after the other, or different condition 1 and another condition 2. So these conditions, I just count how many. So remember, we can just use how many in conditions 1. This symbol to count how many, and then how many in condition 2. And then we multiply these two together. This gives me the number of possibilities that I have. Somebody was maybe saying something. I didn't find the slides. You did not find the slides. Maybe you're looking down. Look up in the middle somewhere. It's up in the middle. Because I did not update it, so it stayed in the middle. I know because I checked. Okay, so let's have another example. I mean, all of these are doing the same thing. Like for example, let's take example number 5. How many different license plates can be made? In each plate contains a sequence of 3 uppercase letters followed by 3 digits. So I have 3 uppercase letters and then 3 numbers. So again, so what are the possibilities? That means each one of them, I have 26 for the first one, 26 for the second one, 26 for the third one. And then here, each one is a number between 0 and 9, which is I have 10 here, 10 here, and 10 here, which is going to be this number, 26 3 times, 10 3 times, and this is going to be the number, possible number of license plates. So that's what this product rule says. Now, again, more examples just to practice that. And there's another type of rule, which is the sum rule, but this sum rule is applicable for different scenarios, different type of scenarios. Now, what's the difference between the product and the sum is that if we have like a task that can be done either in one way or, that's the key word, in another way. So if we'd like to find, okay, how many in total ways that we can do this task for, is that we just add this number of one way and the number 1, number 2. This is actually basically very simple. We use that all the time, but just would like to again make sure that we keep that in mind. And this is what the sum rule says. Like an example, if we have each member of a mathematics faculty or student who is in mathematics major is chosen as a representative of the university committee, how many different choices are there for this representative if there are 37 members of mathematics faculty and 83 mathematics major students? So if we have 37 faculty And then we have 83. That's a weird 8. And we have 83 students, mathematics major. And here they said that no one is both a faculty and a teacher and a student at the same time, which is, yeah, just to make sure that we don't have this case. Then this rule means that if we have this number of ways, and this other number of ways, and they are like there's this joint. That means they have nothing in common. The two ways have nothing in common, because if there's something in common, we're going to see another rule for that. But these two have nothing in common. That means if I would like to know, okay, how many possible candidates to be a representative of the university committee, we just need to add how many faculty members and how many students, because we're going to pick one from all these people. So we just add these two together, which gives us the 120 possibility. So we have 100 possible candidates to do that. So that's the idea behind the sum rule. So this sum rule, what it says is that if you have like two different possibilities to do the same thing, and then this, you just add the number of ways. Okay, maybe more examples. Let's have this one. This is a more complex counting problem. So because that one was basically easy, how about looking at this one? If a version of a computer language, BASIC, well, that's the name of the computer programming language, the name of a variable is a string of 1 or 2 alphanumeric characters. Okay, so that means every variable has only 1 or maximum like 2 alphanumeric characters. Well, alphanumeric characters means it can be a number or a letter or a number. That's what alphanumeric means. So where uppercase and lowercase letters are not distinguished. That means we don't care if it's capital letter or lowercase. We just look at the letter. It doesn't matter if it's uppercase or lowercase. Now there's some programming languages that are like that. So, and can you tell me one that is like that? That you have used for sure. I think for sure that you may have used it. No, maybe not yet. No, maybe not yet. Yeah, but maybe if you know, if someone knows. Java, no, Java, a variable capital letter lowercase makes a difference. If I have a variable x lowercase and x capital letter, it makes a difference. These are two different variables. But they're different. There's some programming languages who don't care about capital letters or lowercase. But you have not seen them yet. SQL is one of them when you're going to see databases. There's also JavaScript, if I remember. Also, JavaScript doesn't make a difference between capital letters and lowercase. I'm not sure though. Don't quote me on that. But I think, anyways, for sure, database SQL is there's no difference between capital and lowercase. So, anyways, now we have a variable. There are two cases. It can be either one alphanumeric character, actually, or two alphanumeric characters. Actually, it says it's a string of 1 or 2 alphanumeric characters. Now there's also moreover a variable name must begin with the letter. So that means if I'm here, it cannot be a number. And also, oh no. And also if I'm in this case with having 2 letters, it cannot be a number here. So it has to be a letter. So it has to start with a letter, which as you see, this is similar to Java basically. And you all know that. So must begin with letter and must be different from the 5 strings of 2 characters that are reserved for programming languages. So you all know, for example, if a variable, even in Java, you cannot name a variable, for example, like int, like double. Why? Because these are reserved words, like private, public. These are reserved words, you cannot use them. But now imagine there are some in this imaginary basic programming language that we have some keywords that are, there are 5 of them that have 2 characters, and these are reserved. So now I'd like to know how many different variable names are there in this version of BASIC. So how many different variable names? So now I have 2 scenarios. I can have this case and this case. So all I have to do is to count how many are this case. This is, sorry, N1, I meant N1. And this is N2, And then what I'm going to do, I have this n1 plus n2 is going to give me how many total possible numbers. So let's calculate the n1. So to be able to calculate this n1, so this is what they do. This v1 they call v is the number of different variables. v1 is the one that has only one character, and v2 is going to be this two characters. So this is our v1 and this is our v2. There's a lot of things going on. So this is v1 and this is v2. So v1 is going to be for one letter, v2 on two letters. Okay, so then what I'm going to do is this v is going to be the v1 plus v2, basically. So, okay, for v1, what are the possible n1 is going to be what? Well, it's going to be a letter, so there's just every letter of the alphabet. So that means v1 is going to be, by default, it's going to be 26. Okay, what about v2 now? Now v2 has two things. The first one has to be a letter, so it cannot be a number. So how many possibilities? 26, because it has to be a letter. What about this one, the second one? It can be a letter or a number. So that means a letter is 26, plus I have, let's say this is 26 plus 10 numbers from 0 to 9. That means this is going to be 36. So in the first one is 26, 36. These two, they're going to be multiplied each other. This is I'm going to apply the product rule, because this first one can be broken into two parts, the first part and the second part, which depend on each other. That's why I'm going to multiply these two together. That means it's going to be 36, 26 plus times 36. But not forget that I said I have 5 among all these 36 times 26 times 36. I don't know what number that gives us. So if I just, let me just multiply that. Okay, where is this calculator? Okay, if I have like 26 times 36, this is going to give us 936. So among these 936, I have 5 strings that are reserved, which means I need to remove from this, I have to remove these 5s. That means this is the number of possibilities. This is just only for v2. So v2 is going to be 931. v1 we said already is going to be 26. So the result of how many possibilities? So it's going to be 26 plus 931, which gives us this number, 957. These are the possible different variable names that I can use just by using one or two characters. So again, this is just counting how many possibilities I can have. And now in this example, we have the sum rule and along with the product rule. So this one is the product rule because we're using two letters within that thing. So we use the product rule, and then we also use the sum rule to have these different possibilities. Is that okay? I think it's not a big deal. Now we have other examples with IP addresses, and which is different class of IP addresses. Now if you took networking, you will have an idea about that, but if you don't, it's just going to be something you're going to see for sure. And yeah, I just would like to move on unless you have any questions. Is that okay for everybody? Clear, inshallah? No issues? All right. Now there's the principle of inclusion and exclusion. This is like the subtract rule. Now, what is the subtract rule? It's actually, if you remember what we said about the summation rule, when there's the sum rule, if I have something and they have nothing in common, so I have two ways to do things, either this way or that way. Now, if there are some ways that have sometimes we have some things that are in common, well, this is where the subtraction rule come into action. Now, what does it say is that if a task can be done in either in one ways or in two ways, but then actually there's something in these two ways that they have in common. So in the number of ways to do task 1 is n1 plus n2 minus the number of ways that to do the tasks that are common between the two different ways. So that's what it says. So basically it's like the sum rule with like they have something in common. Here, the sum rule, we said like this n1 way is totally different from n2 ways. This number of ways is completely different from this one. Now here in this, the difference between this one and that one, this n1 and n2, they might have something in common. Look at it like maybe this is the possible n1, this is also the possibilities, and then n2, they have something in common actually. So if I just do the plus, I'm counting something twice, and I don't want to do that. So that's why we just would like to do the minus, the number of ways that are like common between the two. We'd like to remove this part, so we just count it only once. So that's the idea, because if I count it in n1 and n2, I should not count it again. So this is, if I count it here and then plus n2, that means I'm going to count them also here. So what I need to do, I need to remove it like this, this n1 intersection with n2. I don't know if that makes sense, but because there's a plus, etc. So I need to remove the whatever is in the thing that are between them. And a good example to illustrate that is, for example, how many ways I can have a string of bits or bit strings of length 8. That means I have 8 bits. Either start from with 1 or end with 0, 0. Now if I start with 1, if I count all the possibilities, that means this is going to be 1 for sure. How about this one? Well, I have two options. It can be 2, it can be 0, it can be 1. This can be 0, can be 1, can be 0, can be 1, each one of them. And that's why we have this 1, 2, 3, 4, 5, 6, 7. This is where we get 2 to the power of 7. And one of these is the 0 and 0. So that's why when I do this counting, this 128 ways, it also includes for some of the cases that where they have 2 zeros at the end. So that's why this is also counting. I need to take into consideration the fact that I counted them again when I'm going to add them. Now, the other thing is that now I'm going to count also the possibilities for these two to be zeros. And I have two possibilities here, and then 2, and then 2, 2, 2, and 2. How many 2's? I have 6 times. Again, on this one, I might have the 1 here as one of the possibilities. So I'm going to remove all those that have these possibilities in common. So that's what I'm trying to do. So what are the things in common? So then I need to find, okay, this one, how many ways there are? So they have like 2, 2, 2, 2, and 2. That means each, why I put 2 is that because each one can have be 0 or 1. That means there are 2 possible ways how to have a number here. And then 2 times 5, 2 to the power of 5. So this is going to give me these 32 ways, which means I have 128 ways to have a 1, because remember the question says this one or that one. So it says yeah, this one starts with 1 bit or ends with 2 bits of 0 zeros. So this or here, even though it's the same as the or that was seen before, but this one like is an inclusive or, it includes something instead of like the exclusive. If there were no way that we can have like something in common, we just have this one plus that one. But because we have some situations in common, that's why we need to remove those common so we don't count them twice. And that's what this means. That means I'm going to have 128 plus 64 minus 32, which is going to be this 160. So that's the rule about this subtraction rule, or what they call this principle of inclusion exclusion. So yeah. So these are again some different type of same type of exercises with examples to explain the same thing. Now the last one is a little bit the one that can be a little bit confusing because of the way it is written and what is said as well. It's not actually very easy to follow up. But let's say, okay, if there are some, let's say, X ways to do a task, and if the task can be done using a procedure that carried out multiple ways and different ways, and for every way, exactly this number of times is that this n way can be to be done. So to calculate that, I just need to have this divided by every time on the ways. So you see, it's not really easy even to read. It's kind of a little bit confusing, but let's maybe make an example very clear that's going to make things much easier to understand. So suppose we have an automated system that has been developed to count the legs of cows in a pasture. We count the leg of cows. So the leg of cows is now the n. So n is going to be how many legs of cows do I have. Suppose that this system has determined that in a farmer's pasture there are exactly 572 legs. So we have 572 legs. How many cows are there in the pasture? Now, I know that we have 572 legs. Now, each cow has how many legs? 4. Normally, each cow has 4 legs. So that means what I have to do is to divide this by 4 is going to give me my answer. That is going to be the number of cows. But see how the way it is written, it's kind of complicated. So the n is going to be the number of legs, the cow legs, and then 4 is going to be the number of the ways that I can. The number of ways that each one of the cows is going to be having again. So 572 legs that I have to divide by 4 because each cow will have 4 legs, and this is basically the division rule. So if I give me this, the answer is to divide this by 4, which is going to give me, I don't want to count, so it's supposed to be 143 cows. So that's basically the idea. So you have a number that you have a divide by another number to give you the number of possibilities. So that's why they call it the division rule. Now let's have a look at another example. Oh, there's not an example. Oh, too bad. Maybe let me give you another example. Is it? Yeah, maybe that other example might be a little bit too complex, but let me try it. Okay, let's try another example. The other example would be as follows. Let's say I have a table. That's actually, I'm taking that example from the videos that I attach also in the resources you can find. So let's say in that example, I have like a table, and each one of the tables I would like to, now how many, I have to have 6 guests in them. 1, 2, 3, 4, 5, and 6. So now the 6 guests, how many ways are there to put those 6 guests? And also what I would like to maybe having is that I don't want to have the same guests should not have the same neighbors. A, B, C, D, E, and F. These are the name of the guests. So because each time I have for the A, so how many possibilities that I have to have the A to be seated? Well, because I'm going to sit A first, I have 6 possible places for A. Now B, after the B I have 5 more, because now the one A took 1, so I'm going to have 5. For C, it's 4. For D is going to be 3. For E, I have only 2 options. And then for F, there's only 1. And notice that this is going to be actually 6 factorial. Now, if I do this, I can say, oh, then, okay, this is the number of possibilities. But no, what happens is that when I say that A has 6 possibilities, well, maybe if you put A not here, but you put it here, and then B here, it's going to be, maybe let me try with a different color. Let me move this around a bit. This one, let me try a different color. So for example, if I put A here, now B here, and C and D and E and F, they still are the same. They have each guest have the same neighbors again, and that means each one is actually going to be seated the same way. Now, if my condition, if I say, okay, I don't care if they are seated the same way, no, I don't, this is going to be the answer. But my question is that this is all the possible ways, but among all the possible ways, I don't want them to be actually having the same neighbors. So to see that, well, basically how many possibilities that I can put these together, because this A can be here, or here, or here, or here, or here, or here. And if I just keep rotating the whole guests, this is actually the number of time, the possibilities that I can have this. So the actual answer is going to be, if I have this divided by 6. So I have these total possibilities, and then they divide by the number of ways that I can just, again, rotate them together to have the same result. And this basically is going to be like 5 factorial. Because if you have this whole thing divided by 6, you just remove 6, and it gives you kept with 5. Anyways, I hope this example helps. But the idea is that if you have this kind of situation when you have a big number and then some kind of ways how to repeat that same number. So these number of cows have 557. These are all the legs, and you have a way how to take the number of legs to count something, and that's the basic idea how to divide this by the number of legs that we have to get the right answer. Okay, there's okay, another way how to count. Maybe there's this tree diagram, this is again another way maybe to see or to represent visually some of those possible to count some possibilities. Now we have this here, for example, how many bit strings length of 4 do not have two consecutive ones. So if I don't want to have two consecutive ones, basically, so this says with the, well, I need to start with 0 and 1, so there's no consecutive ones, so I have two zeros and ones. Now here for zeros and ones, I can put another 0, I can have 1, because my problem, I don't want to have two consecutive ones. So I don't have two consecutive ones, that's fine. But here, for example, after checking the 1, I have another option. I don't have any two options. I don't have like 0 and 1 like the others have. Here, as when there's 1, I have another option. It has to be 0. So I can put only 0 here. And then when it's 0, I can have 0 and 1. So all you have to do is every time you have this 1, then the next option possible is going to be like only 0. There's no 1. You're not going to draw them like this. So that's actually the way to represent this. And then all you have to do is you have to count how many paths we have. I mean, the whole thing. So they have 1, 2, 3, 4, 5, 6, 7, 8. So for a bit of 4, that's the constraint. I have 4 bits. Then there are 2, 4, 6, 8 ways to have a combination where there are no consecutive ones, two consecutive ones there. I can not only use it for that. Maybe let's say if I have, okay, if I have, let's say 5 shirts. Oh, let's make it easy on me. I'm going to make it like 3 shirts. 3 shirts. And 2 pair of shoes. Okay. Now, how many possible combination of shirts and shoes that I can have? Well, it's the same logic again. I'm just going to have, this is the shirt one. I'm going to have this is S shirt one. Maybe it's shirt one. Let me just call it shirt one, and SH on shirt 2 and shirt 3. Each one of them I can have like, this is the shoe 1, shoe 2, and then each one of them is going to be having shoe 1, shoe 2, and same thing, shoe 1, shoe 2, and then I just count how many there are. So I have 1, 2, 3, 4, 5, 6, which actually basically just gives you the 6 number of possibilities, because this is the case. But sometimes it may be easier to have this tree diagram representation to count, and or maybe just to double check that you have the answer is right. So that's a way how to do that. So same thing here. There's another example. I have a t-shirt that has this type of sizes, and each size, this size comes with 4 colors, except for each we have 4 colors except for the XL, which comes only in red and green and black, and XXL, which comes only in green and black. So now if I'd like to count how many possible things, so all I have to do is I have to represent all the different sizes. I could also have started with the colors. It doesn't matter. I could also have started with the colors. It's not a problem. I'm just going to end up with the same count, not the same tree, but the same count. So we said for the small, medium, large, for all except for, so I have this small, medium, large, all of these, they come in 4 colors, 1, 2, 3, 4, except for XL, which comes only in 3 colors. So this means small, 4 colors, medium, 4 colors, large, 4 colors. Now XL comes on 3 colors, which is the red, green, and black. So this we have red, green, and black. And then also the XXL comes on green and black. So I'll just represent that. And then you can count now how many possibilities there are. So this is a way how also to do the counting. And that's pretty much it for this part over here. As you can see, there's not actually much of it. It's not very complicated, but let me just maybe summarize it. Let me go back up. So what we have seen is that we have the product rule when we have two things that depend on each other. The one, then the other one is coming after the first one, and we do the product to count how many possibilities. And then when they are actually different ways how to do things, this way or that way, and then we count the total number of ways. We just sum them up, assuming that there is no common way between the two ways. If there is a common way between the two ways, then this is coming back to this subtraction rule, which is going to be the number one way plus number two ways, and then I need to subtract minus whatever they have in common, the common of the two ways. And the last one we've seen, besides before just the three representations, is about the division. When you have a number of ways that can be divided by the same number to count how many times this thing happened, and we're just going to do the division, basically. I'm just trying to find a different way to read this, because this if you read it this way, it's not very easy to follow. Any questions? I mean, you have these the answers. Also, you have these ways how to do that. Okay, I'm not going to go through that. I'm just going to actually maybe update the slides to make them disappear. All right. So it's basically very easy. I mean, this week's topics is very easy. Maybe the next week is going to be slightly more details about it, but or maybe requires a little bit more time and attention. But this one is kind of very easy. Now, there's the last thing we're going to be seeing today is this pigeonhole principle, which is a very basic also, that seems sometimes so obvious, but this has actually some implications that are going to allow us to prove things or to add different things, and to come up also with different scenarios. Now, this pigeonhole principle is very simple. Now, if you have whatever number, let's say here we have nine boxes where each one of the boxes a pigeon can go into. Now, what this pigeonhole principle says, now if you have 9 here, and then you have 10 pigeons that are going to go and try to fit into those nine boxes, well, there's no way that each one of them is going to be only having one. Well, maybe generally each one is going to go for the empty one, but when they're all going to be full, the last pigeon is going to find a place and just pick one and complete it. So what does it mean is that in this pigeonhole principle, if we have 10 number of something that goes into just 9 places, well, what it says is that one of the places is going to have more than one. So that's what it says. So that's the idea, is that pigeonhole principle is that if there are more pigeons than pigeonholes, then there must be at least one pigeonhole with at least 2 pigeons in it. So that's the principle. If k is a positive integer and k plus 1 or more objects, so k is more than k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects. So that's what we were saying. If k is like we have 9 boxes, k is 9, and we have 10 birds that goes into those, so that means one of the boxes contains 2 or more of the birds. So that's basically the idea. And then from that, we can deduct that a function f from a set with k plus 1 or more elements to a set with k is not 1-to-1. Okay, so just maybe not big a problem. Let's say I'm going to simplify my pigeon to something like this. My pigeonhole, I have 4 boxes and I have 5 pigeons, 5 birds. Now what does it say? That means I'm going to have a bird here, a bird here, a bird here maybe, and then one bird here. Another one, the last one, the 5th one, is going to try to choose a place, and then maybe I'm going to have another one here. So there are 2 birds now. So one here and one here. So each one of them, well, that's It's supposed to be a bird. So anyways, so that you get the point. So what it means then, if the function from a set that has k plus 1 elements, I have a function here from a set that have these 5 birds, going into a set that has 4 boxes. Let me just maybe put the boxes like this. Okay, let me just remove those dots to avoid any. That would be better. So I have 4 boxes, but I have 5 birds. There's no way that it's going to be a one-to-one. Remember the definition of a function that is a one-to-one? That means for every element in, remember what's the name of this? When you have this function, the set is called, okay, let me give you a hint. One of them is domain, and the other one is codomain. Which one is the domain, which one is the codomain? Do you remember? Without trying to look back at the slides or something. Okay, who remembers? The next one is the codomain. So this is the codomain, is that right? So this is the codomain, this is the domain. Is that it? Only one brave. Yeah, well, just confirming yourself. What about the others? Anyone concurs? Agrees? Disagrees? Yes, you all agree? Are you sure? Yeah. And okay, what about this one here? This one here, an element from here is called what? This is a good review for like functions. That one over here is called what? Good job. Image. What about this one? Pre-image. Well, good. That's great. So anyways, that's what it says. Because I have one extra, if I have a function that takes me from a set with k plus 1 to a set with k, then it's not going to be able to be one-to-one, because one-to-one means each one has going to only one. Now we're going to have to one that goes actually to more than one. And that's the idea. So that's why also we have this kind of example that says among any group of 367 people, there must be at least 2 with the same birthday. Well, assuming we are working with the common year of 365 or something like that. Or the leap year is going to be 366. So that's the, yeah, that's the thing. So that's basically the idea behind that. Another example is that in any group of 27 English words, if I have 27 English words, there must be at least 2, I say at least, that begins with the same letter. Now, if I have 27 English words, that means the first word starts from A, the second word starts from B, all of them. C, this is the worst case scenario, because I might have A and A and A, multiple, whatever. But I'm saying in the worst case scenario, it must be at least, if each one of them has a word that starts with A, another word that starts with B, and I got all 26 of them until the word that starts with Z, to make the 27th, well, I have to pick one that was picked before. So that's the idea behind this. So so assuming the worst case, assuming the worst case, every word begins with the different letter, then at least one word, I'm going to have 2 words that begin with the same letter. So that's the implications of having this pigeonhole principle, which might look like, okay, that's obvious, but yeah, but this is something that helps us in this way. And then there's this theorem that we can maybe finish with it. The generalized pigeonhole principle, which says that if n objects are placed into k boxes, now my n objects, let's say 10, or maybe let's keep it simple so we don't have, okay, let's say I have my 5 birds into 4 boxes. then there is at least one box containing at least this here. Now this here is called the ceiling. So the ceiling of n divided by 4. Now 5 divided by 4 is going to give me 1 point something. I don't care about the thing, because I'm looking at the ceiling, that means this thing is going to be 2. So what it says that if I have 5 objects are placed into 4 boxes, then there is at least one box containing 2 objects, at least. Now this rule applies to anything. If I have 20 birds that I have only 4 that goes onto 4 boxes, then so what's going to be the result is that 20 divided by, let's make it 5 so it won't be much easier. 20 divided by 5, that means it's going to be 4, and the ceiling of 4 is going to be also 4. So that means if I have 20 birds going to 5 boxes, there's at least one box that contains 4 birds. Well, at least one. It doesn't mean, in this case, if we did 20 divided by 5, they can have like maybe go into different places. All of them are going to be 5. So that's the basic idea that can be applied to a lot of different examples. Now this can be a little bit more complex, or if you have, for example, you play with this to play with the cards, so they have this kind of examples, but I'm not going to go through that. You can go through that if you want to practice more, or maybe, for example, okay, let's do another one. We still have maybe a few minutes, and then I can give you the mini test, inshallah. So what is the least number of area codes needed to guarantee that 25 million phones in the country can be assigned distinct 10-digit telephone numbers? Now assume that the telephone numbers are of the form NXX, NXX, XX for X's. Now first, the first 3 digits form the area code, this one. This is the area code. N represents a number from 2 to 9 inclusively. That means N, that means from 2 to 9. X represents any digits, that means from 0 to 9. That means here in N, I cannot have a 0, I cannot have a 1. Now this is some kind of code. So now how to know what is the least number of area codes? Now what is the area codes? We said that the first 3 digits constitute the area code. So to look for this removing this area code, if we just take this part over here, this is the one here. So what are the possible combination of numbers that I can have? Now I'm excluding the area code, so just to have a look, this is 8. Why 8? Because from 2 to 9 I just removed 0, I removed 1, so 10 minus 2 is going to be 8. I have 8 possible digits, and then the rest are 10, 10, 10, 10. So this is the first 3, and these are the last 4. So this is going to be 8 to the power of 10 times 10 to the power of 6, which is 1 million. That means it's going to be 8 million. Now, by the generalized pigeonhole principle, among 25 million telephones, at least we can have 25 million divided by 8 million. This gives us like 25 divided by 8, which is going to be, again, with the floor. So this is going to be 25 times, 8 times 3. It's going to be 3 point something, because 8 times 3 is going to be 24. So 3 point something is going to be that. So this is going to be the ceiling. That means I'm going to get the next integer of it. That's going to be 4. So then if we have that, they must have identical 4 must have identical 4 numbers. So there are 4 area codes that are required to ensure that these 10 numbers are different. That means if we'd like to have 25 million different numbers, we need to have 5 different area codes that with these things. So this region is going to be having 5 different area codes. So that's the example of usage of this pigeonhole principle. So yeah, that's pretty much it. We can have like more exercises. Sorry, I forgot. I didn't have time actually. I forgot. I thought I did it, but then I realized I didn't do it. I didn't do them. I like to remove those answers so you can just practice, but I didn't do that. So you have to maybe be jungling. Or inshallah, by the end of this evening, I will update the slide. So if you'd like to try to do that later, you could. Is that okay?